You built an app. 10,000 people just tried to use it at the same time. What happens next? Today we find out. Welcome back. We're starting a deep dive into load balancers. 3 parts. This is part 1. By the end of this video, you'll understand why every serious web service needs a load balancer, and what one actually is. Quick definition before we dive in. A load balancer is software that sits between your users and your application servers. It takes incoming requests and distributes them across many machines, so no single server gets overwhelmed. Today, we'll cover 3 things. Why one server fails at scale, how a load balancer actually works, and the Layer 4 versus Layer 7 distinction every system design interview asks about. Let's start at the beginning. The simplest possible setup. You have a server. You have users. A user types your URL into a browser. The request travels to your server. The server does some work. Maybe queries a database, maybe runs some logic. Then it sends back a response. When you have 10 users, this works fine. When you have 100 users, it still works. Your server is doing about 100 requests per second, which is well within what a normal server can handle. If you've ever built a side project and deployed it, this is what your setup looks like. One server, doing the job. But what happens when you go from 10 users to 10 million? Let's look at what's actually happening inside the server. Every server has finite resources. CPU, how much computation it can do per second. Memory, how much state it can hold at once. Network bandwidth, how much data it can move in and out. Each request consumes some of each. When requests come in faster than the server can finish them, they start queuing up. Latency climbs. Users wait longer. Eventually the queue fills up. New requests get dropped. Then memory runs out. Then the server crashes. The instinct here is to buy a bigger server. More CPU, more RAM. We call this vertical scaling. And it works, up to a point. But there's a ceiling. The biggest single server on Earth can't handle the traffic Netflix gets in 1 second. And bigger servers cost exponentially more. You hit a wall where you're paying 10 times as much for twice the performance. There's a better idea. Instead of one massive server, what if you run many smaller ones? 5 regular servers, side by side, each handling some of the traffic. Need more capacity? Add another server. And another. We call this horizontal scaling. The math is in your favor. 5 servers cost about the same as one server that's 5 times bigger, but they're more reliable. If one crashes, you still have 4. But here's the catch. Your user types your URL into a browser. Which server do they talk to? They don't know. The browser only knows your domain name. It needs one address to connect to. But now you have 5 servers, each with their own address. How do we hide all that complexity from the user? We add one more piece. We put a box in front of all our servers. We call it a load balancer. Think of it like the receptionist at a busy office. Visitors walk in. They don't know which agent is free, or which agent handles their type of request. They just talk to the receptionist. The receptionist says, "Agent 2 is free, go talk to them." That's exactly what a load balancer does, but for web requests. Users connect to the load balancer. The load balancer looks at its pool of backend servers, picks one that forwards the request. The user never knows there are 5 servers behind the curtain. To them, it's one address, one service. Let's slow this down and trace a single request from start to finish. Step 1. User types yoursite.com into their browser. Step 2. The browser needs to find out where yoursite.com lives on the internet. It asks DNS. Think of DNS as the internet's phone book. You give it a domain name, it gives you back an IP address. Step 3. Here's the trick. The IP address DNS returns is not your server. It's your load balancer. Step 4. The browser opens a connection to that IP address and sends the request. Step 5. The load balancer is now holding a request that needs to be processed. It checks its pool of healthy backend servers. Picks one. Let's say server 2. forwards the request to server 2. Step 6. Server 2 does the actual work. Runs your application code, maybe queries your database, builds the response. Step 7. Server 2 sends the response back through the load balancer. Step 8. The user sees the page. From the user's perspective, they made one request and got one response. They have no idea 5 servers exist. Now I need to explain something before we go further. Because the next thing we'll discuss is layer 4 versus layer 7. And if you don't know what a layer is, that's going to sound like nonsense. Network communication happens in layers. Each layer wraps around the data from the layer above it, like nested envelopes. At layer 3, we see IP addresses, the where. At layer 4, we see ports and connection state, the which conversation. At layer 7, we see the actual data, HTTP requests, headers, URLs, JSON. The what you're saying. A piece of software can choose to operate at any of these layers. The deeper it looks, the more it knows. But the deeper it looks, the more work it has to do per request. Now we can talk about layer 4 versus layer 7 load balancers. A layer 4 load balancer operates at the transport layer. It sees the source IP, the destination IP, and the ports. That's it. It doesn't open up the actual content of the request. Think of it like a mail sorter who only looks at the address on the envelope. They don't read the letter inside. Layer 4 is fast because it has very little work to do per packet. AWS sells this as the network load balancer. A layer 7 load balancer operates at the application layer. It actually opens the request, reads the HTTP headers, sees the URL, sees the cookies. Now it can do smarter things. Send requests for /API to your API servers. Send requests for /static to ACDN, detect mobile user agents and route them to a mobile optimized cluster. Like a mail sorter who actually reads the letter and decides where it goes based on the content. AWS calls this the application load balancer. The trade-off is speed. Layer 4 is faster but blind. Layer 7 is slower but intelligent. For most modern web apps, you want layer 7. The flexibility is worth the small latency cost. Quick recap. One server breaks at scale because its resources are finite. Running many servers fixes the scaling problem, but creates a new problem: how do users find them? A load balancer solves that. It hides all your servers behind one address. And there are 2 flavors. Layer 4 is fast and blind. Layer 7 is smart and slower. That's the foundation. You now understand what a load balancer is, and why it exists. In part 2, we'll get into the actual decisions the load balancer makes. How does it pick which server gets each request? What happens when a server fails? Subscribe so you don't miss it.